This is the NASA Johnson Space Center, home of America's astronauts and control center for the nation's manned space missions. It is also the center for a team of highly qualified aerospace engineers who are shaping tomorrow. But before we have a closer look, let's see if we can answer a few questions like,
what is an engineer?
What does an engineer do? At what point does an engineer start to specialize?
Will the field of engineering decrease as more people study or go into the field?
What type of background and knowledge must an aerospace engineer have to obtain a good job with a place like NASA or McDonnell Douglas?
What are the newer fields of engineering?
And what does a biomedical engineer do at NASA?
people know what firemen and policemen and doctors do. But what about engineers? Let's talk to some engineers from NASA's Johnson Space Center to see if we can find out how they became engineers and what they think is important about their jobs.
This is the ATM Science Room. During Skylab, we monitored the Apollo telescope mount from this room. This console monitored the white light coronagraph, which was an instrument to look at the sun in the visible spectrum. The coronagraph worked in such a manner that there was a disk which blocked out the full face of the sun, and we were really interested in what was called the corona. This was a big mass of material, and we were able to capture with the white light coronagraph. During Skylab, we had to work with scientists across the United States and help them design scientific instruments which would study the sun. We designed those instruments from an operational standpoint. The scientists designed it from a scientific standpoint, knowing what their scientific objectives were. We got involved and helped them to design the instruments in such a fashion that they would be controllable from the ground. We could look at the right type of data from the spacecraft and sit at the consoles and determine how the instrument is operating, where to point the instrument, what to do with it, correct for any malfunctions that occurred during the flight. I got interested in engineering back during my high school days when I was influenced by my teachers, my parents. My father was an automotive mechanic, and ever since I can remember, I've been interested in mechanical gadgets, repairing them, taking them apart. And I thought at that time I wanted to be an automotive engineer. However, during my senior year in high school, I had a research project assigned to me in a chemistry class, which involved determining or finding out how a gadget worked called a cyclotron. During the process of that research, I found out that this instrument was something used in the field of physics, some magic field of physics that split small particles, atoms, into smaller parts. So I then became interested in this field of physics and decided to go to college and major in the subject of physics. In 1963, I started working at the Johnson Space Center with a group responsible for designing the lunar module, the spacecraft which landed on the moon, and later was assigned to a group to study the lunar surface and to try and find suitable landing sites for this lunar module. In 65, I was graduated, and at that time, or during that time, is when I sat at this console and monitored the Skylab mission.
Coming from a poor family, my dad certainly couldn't afford to send me to school, and the only way that I could go was if some way I was managed to get the money, either through a scholarship or through the military, which is one of the areas that was certainly open to me. And I went ahead through school, and I finally got involved in the classes such as in math and science and physics And these are courses that I really enjoyed. And the thing that distinguished the students over in the math and the physics area, these type of scientific type courses was that, hey, if you're taking these kind of courses, you're able to say that you're different from the average type student which is taking the related math courses or the easy way out through school. And this was a challenge to me to be able to say that I was taking the hard courses and was still able to get the grades. And this was important to me as far as a goal in life. I always wanted to be able to do good in school. And once I got through my junior year in high school, I had taken most of the courses that would make me able to go to college. And I had always been interested in electricity, and it kind of fascinated me. And playing with radios when I was smaller had helped me to have respect for electricity and engineering as a whole. And so I stayed with engineering all the way through school. And finally, when I graduated in '74, I came to work here at NASA. And I've been here for now 2.5 years working with the electrical distribution system of the shuttle itself. And we're in charge of making sure that the right amount of power gets to the right places. Now, Charlie works in the other section, which is the equipment section. They're in charge of the components themselves, the testing of the components.
Just to go through the chronology of what it takes to be an engineer here. Take one of my components, maybe the remote power controller. We start out with a vendor coming in with the conception. They think they've got a design that's going to do all the great things for the space program. So they come in and tell us about their design. We have to look over the design, so you have to have some engineering background, and you have to keep up with state of the art, because when people are coming in with something new, it's really new. You have to know the state of the art at that time. So they come in with this idea. We have to look over their design and say, yep, I think it will do what we want it to. And we go on contract to these people to maybe make us up some prototypes. And they bring those prototype models in. We take them out in our laboratory and run evaluation tests and see if they really perform as they're supposed to. Once they get all the bugs out, we go up to management and say, these people have a real good idea. It's going to save us money, and it's going to save us space and weight, which is, our primary concerns on the shuttle. Well, we have to attend design reviews to make sure they're doing all the things that we need to have done. We have environmental requirements that are different from what the average industrial person might require. And we have to know something about their manufacturing techniques, because we kind of have to foresee any problems that might show up later on. When we've launched something out in space, we can't have any baddies happening. So you have to have a pretty good background. You have to know something maybe about a little business. You have to know a little something about production, and you have to know something about engineering. So it takes a varied background to do work here.
Other NASA engineers are looking beyond the year 2000.
I'm an electrical engineer here at the Johnson Space Center in Houston. Right now we're located in Building 32 in a vacuum chamber. And this vacuum chamber here is probably the largest in the free world. It's an engineering test unit designed to simulate the conditions in outer space. It's approximately 120 feet high, 65 feet in diameter. And this door alone here weighs about 40 tons. But for the moment, I want to talk to you a little about how I got into engineering. I grew up in a small town in Central Texas, and my childhood experiences weren't very much different than what you have experienced. As a kid, I was a neighborhood bicycle mechanic, got involved in other activities involving fixing carburetors on automobiles and so forth. Well, my interest in engineering only flourished after I got into high school. I had a high school math teacher who more or less explained to me what engineering was all about and encouraged me to pursue that field. Right now, we're looking at systems which will collect energy from the sun, beam it back to the earth in the form of microwave energy, and convert it to electricity to be used by people like you. These systems are aimed at solving the problem we have in energy right now. It gets us away from using coal, oil, and natural gas, natural resources that are in short supply. In addition to collecting solar energy from space. In the future, we're going to be looking at using space in other ways. Perhaps by the year 2000 to the year 2025, we'll have colonies of people living and producing in space. We'll have manufacturing production facilities in space. At this point in time, I probably won't be here or even involved, but you will. And these are going to be the kind of problems that are going to be left to people like you and your peers to solve.
Let's talk to a biomedical engineer and see what that job's like at NASA.
I was really interested in the space program, so that's what I started really working towards, was trying to get into NASA and working for NASA. I took all the prerequisites for all the science and engineering courses in high school. Once I got into high school, I took just mostly science courses, and my major was in biophysics. That really is also made up of a lot of biochemistry. I have a minor in chemistry, and a lot of physics courses, and a lot of mathematics courses. Started getting interested into the engineering aspects of it when I started to look at NASA more seriously, and when I started looking for a job with NASA. I am currently taking courses at the University of Houston as a graduate student in electronics, and I think my field has started to be more into the electronics background now. Some of the things that I've been working here at NASA have been 3 cardiovascular experiments that had mainly to do with fluid shifts in the cardiovascular systems and the way that the blood circulated within your body in 0G. Now, here before you see the lower body negative pressure device. A device just like this one was flown in Skylab. What this device did is that the person gets in it and the legs first, and it seals at your waist. Then we reduce the pressure within the module. And zero gravity, since you have no gravity pulling down, all the fluids in your body really collect around your thorax and your head. Well, this puts a great strain on your cardiovascular system. We'd like to be seeing what type of stresses the astronauts are exposed to. We're taking EKG, blood pressure, and then we've got these capacitance bands that we put around the legs, and these would measure the difference of cardiovascular effects both in zero gravity and here on the ground. Before an experiment is actually flown, it goes through a series of tests. Some of the tests that we do is to fly it in the 0G aircraft. This aircraft performs parabolic flight, and there's a state in the parabola where you are in zero gravity. Now in there we test similar equipment to this and other experiments. In January of 1975, we had a space lab simulation in which cardiovascular experiments and other types of experiments like vestibular experiments, rat experiments, plant experiments, where the hardware was tested out. Not only did we test out procedures, we tested out the crew procedures, the hardware itself, and the timelines and the power that it took for the experiments.
This engineer is working to see that when payloads are constructed for the shuttle, they will fit and work well with the shuttle systems.
One of our prime responsibilities in the program office is to make sure that as the development of the space shuttle is completed, to try to integrate various payloads into the space shuttle. The space shuttle here shows a payload bay, and the payloads are those pieces of hardware that have been developed out in the scientific community. An example of some of the payloads that will be flying on the space shuttle are the Space Lab, which is a carrier that is designed by the European countries. And once the Space Lab is designed, it will be flown on the space shuttle. I think that not only should one be good in the field of math, physics, or chemistry, but he should also be good in English, you know. He should be good in writing, because it is very important that one be able to communicate with people the ideas that he has been able to come up with. And if he's not able to express or get his thoughts over to the person that he's trying to sell the idea, the math and the physics, in my opinion, really doesn't help him. So I think that if the person is good at changing the oil on his father's car, if he's good in the field of mathematics, if he's good with just doing things with his hands, if he wants to be a builder, I think that this is an interest that is generated from within. And I think that that's the most important thing. I think the most important thing is to be in an atmosphere whereby one can be exposed to the field. And once he's been exposed, I think it has to be left up to the student. It has to be generated from within as to the kind of person that he wants to become.
Solving problems, making choices. Only you know if you want to be an engineer. But if you make that choice, the doors are open to go as far as your imagination will take you. In just 60 years, mankind progressed from that first short flight at Kitty Hawk to that giant leap to the moon. And beyond that now, to the routine access to space with the space shuttle. This achievement was attained by a team of specialists who, perhaps like you, wanted to play their part in shaping tomorrow.